All right, folks, it is 7 o'clock, so I think that means it is time for us to get started. We are so happy that you've decided to join us. We'll have our experts start their camera up so that we can give you all a little hello and start off with an introduction. So excuse me. Thanks for being here tonight, folks. My name is Talia. I am the Virtual Experiences Coordinator at the Denver Museum of Nature and Science, and I am so excited to yet again be your host and moderator for this next installment of our Digital Earth series. If you've never been a part of Digital Earth before, maybe you have and you already know this, but I'll say it just because it's so much fun to get to say these words to all of you. Digital Earth is a series in which we take you on a digital virtual journey all around our planet Earth, and sometimes even taking you to other locations in our solar system. So tonight we're focusing on plate tectonics and some of the marks and features on our planet's surface that have been shaped by the moves of the tectonic plates all across our planet's surface. So our two experts that we're connected to currently via Zoom, so Dr. Chun Yu, who is our space sciences curator, and Dr. Bob Raynolds, who is a research associate and geologist. They're going to take you on a journey. They're going to be your tour guides and your pilots, and they're going to tell you all about features and places on planet Earth that, of course, we can't get to physically, but the power of technology allows us to reach digitally. A couple of quick housekeeping items before we get going. Tonight, you can use the chat to communicate with us. So we cannot see you or hear you, but that doesn't mean you can't communicate. We're gonna have an eye on the chat tonight, and that's where you can share any questions, comments, stories that you have. We love for these events to feel almost like a conversation, like a fireside or a living room chat. So if you've been to any of the places that we're gonna talk about tonight, we do, of course, wanna hear about it in the chat. If you have any questions, any cool connections, any comments that you wanna share, pop them in the chat. We will be watching. So please do let us know what you got tonight. My role, once our presentation is done, once our tour is done, will be to bring your questions to the experts. So I'll be watching all night long, and we may even be able to pull your question at the end. If you're wondering where all of these messages are that I apparently am seeing, we do have it set tonight so that your messages are going only to us, the panelists and hosts of the webinar. So that's an added security and privacy feature that we did on purpose. So no worries if you're not seeing each other's messages. We're seeing it, and that's what really matters. So we're going to be able to pull those questions to ask our experts at the end of our presentation. Without any further ado, I am going to read out our first haiku of the evening. That's right, if this is your first Digital Earth, we have a fun tradition that started several weeks ago. Judy in Fort Collins sent us a haiku about one of our programs, and people have been sending us haikus in the chat ever since. And Challen is revealing the answer to one of our other Digital Earth traditions, which is guess what's in my virtual background. And so, Challen, our first haiku is, huge rift in the ground spans the entire west coast, high San Andreas. So this is in fact the San Andreas Fault. That was our first geologic feature that we're going to talk about. Well, that I'll mention. Our experts are going to start us a little bit elsewhere on our planet, but we will eventually get around to that one too. So without any further ado, it is my distinct pleasure to introduce Dr. Chun Yu, who is our curator of space science. He's going to tell us a little bit about how we actually take you on these fantastic virtual journeys. Chun, how you doing?
I'm doing pretty well. Thank you for that great introduction, Talia. Well, hello, everyone. For those of you who haven't been to one of these, Digital Earth is a program that we've actually been running at the museum for over 10 years. And normally it takes place in the Gates Planetarium. But because of what's happening right now, we're doing it live and over the internet so that we can have a lot more people enjoy it from all across the country. And normally you think of the planetarium as a place where you can that you go to explore the universe. But the software that we use not only allows us to fly out into distant space, but it also allows us to turn our gaze back down towards our home planet. And that's what Digital Earth is all about, giving us and our guests an astronaut's perspective of our planet Earth and to see what the Earth looks like from space. And the software that we're using is something called OpenSpace. Let me turn this on now. And OpenSpace is a project that was started at the American Museum of Natural History in New York. And they are funded by NASA, and we are a partner on that grant. And it's the imagery that you're seeing is based on real satellite imagery. And so here we're seeing clouds on the Earth that was taken about a week ago, but I can actually turn the clouds off. And so we'll be turning the clouds off and seeing the Earth cloudless. And you can imagine that it's very it can often be difficult to find a cloud-free portion or a period of time in which you can take a picture of parts of the Earth. So this is the images that you're seeing have been assembled from years worth of satellite data. And every now and then, we might even turn the atmosphere off to make things clearer. But what you're seeing is all based on real scientific data returned from satellites. And as Talia mentioned, we will also be flying elsewhere in the solar system where we see tectonic activity. And I'll leave it up to you to guess where that might be later on. But for those of you who might be interested in downloading and using the software, this is still very beta software, so it's not very easy to use. But for those of you who are courageous enough to do this, I encourage you to go to openspaceproject.com to find a download. And otherwise, you can always check out Google Earth. That's also widely available. So with that, I want to turn it over to our main speaker, Dr. Bob Raynolds, a research associate in the Earth Sciences Department at the Denver Museum of Nature and Science. So Bob, take it away.
Yeah, well, thank you, Chun, and thank you, Talia. It's a wonderful opportunity to join you guys, and we're all coming from our respective basements as we do this programming. So it's a little bit of a new thing for us, but we're learning how to use the technology and how to make good use of the virtual connectivity that we have. It's a wonderful series of tools. One of the things that I like to think about as a research associate at the Denver Museum, where I'm a geologist, I work with the Earth Sciences Department, is that the museum is an organization, an institution really, that provides context for our life on Earth. And at the Denver Museum, like many other natural history museums around the world, we have a huge collection of material, much of which is, of course, in our archives. But, of course, a huge amount of material is on display. And one of the things that we are very proud of at the Museum of Nature and Science in Denver is our collection of fossils, the paleontology collection, and also our collection of minerals, the Coors Hall of Minerals. And with these collections that are both in storage and on display, we provide really a global context for our civilization. We treasure these specimens and the features that we curate, and we consider the role of museums as being sort of a deep keel in the turbulent waters, if you will, and we conserve the legacy of the scientific data sets for our civilization. It's a really wonderful challenge and opportunity. So my hats off to all museums around the country and around the world that are struggling in these times. What we're doing this evening, though, is a good example of what can be done with innovation, where although the museum is just barely opening up in Denver, we were able to reach out to an audience of hundreds of people with our technology. And we're going to start out this evening. First of all, the overall program is continental drift or plate tectonics. So we're talking about what's the surface of the Earth made of, and we're all riding on these semi-rigid plates that are that make up the Earth's crust. And tonight, what we're going to do is explore the patterns that we can see from space. So we're looking at the first order patterns. These are the patterns that really define the shape and the landscapes of the Earth as a whole. And what we're going to be doing is discussing the character of the geometries that we see. I'll be talking about the reason why the geometries are there, talking about the underlying forces that have made it happen. But what I want you to think about is that these patterns are global, and we might see a pattern in one place and recognize a shape or a configuration. Then we might go to another place where it might be a lot more subtle. And because we've seen the pattern in a place where it's more clearly evident, we can make an educated guess or interpretation of the place where it's more subtle. So the science of geology, which is often called an eclectic science, but because it uses many different disciplines, but we really study patterns of the Earth, patterns of Earth history, patterns of behavior. We used to say that the present is the key to the past, and that was always a little bit of a joke amongst geology students, because we'd study the present conditions and try to interpret the past. And now, in interesting situation, we're looking at many past environments and trying to predict what's going to be happening in the future as we go into a time of climate change. So some very interesting things happening in the field of geology. But let's start out, Chun, we might start out with a view of the South Atlantic. And we're going to start out big, and then we're going to zoom in close to an area. So when we start out with the South Atlantic, We're looking at a view that you've all seen, and I can remember when I was a youngster, I was in grade school, I think probably in first grade, and there was a globe sitting on the side of the room. And of course, I was sort of daydreaming and looking at the globe. And in those eras and times, we were all puzzlers and we made puzzles. And I think that a lot of you have seen this view. And even before you took geology classes, you might have speculated about the curious coincidence of the shapes of the eastern side of South America and the western side of Africa. And of course, it's accentuated once you have a globe like the one that Chun is revealing, where you can see a sense of the mid-ocean topography. And you'll see that there's a mountain range that runs down the center of the Atlantic Ocean. We call it the Mid-Atlantic Ridge. And indeed, there's a tremendous amount of symmetry here. The coastlines do fit together. The geology of South America matches the geology of Africa. Lots of stories there about the different fossils and how this was all put together, starting largely with a fellow named Alfred Wegener, but many other people observed the same patterns. And what we're going to do now is we're going to go to an area where we'll use the same kinds of patterns, but we're going to use it as a template to understand this phenomenon of continental drift. And we're heading over towards the Red Sea, and we're going to cross Africa, and we're going to get ourselves over to a good view of the Red Sea, the Gulf of Aden, the Arabian Peninsula, and the Persian Gulf, the Straits of Hormuz. And the geography here, just to keep you oriented, you've got Africa on the left, you've got the Nile River, you might be able to pick that, running up to the north. And then you've got the Red Sea extending from sort of upper left to lower right. The Gulf of Aden is at the bottom. The Persian Gulf is in the upper right. And the Arabian Peninsula is in the main center part of the screen. And what we're going to do in the course of the next few minutes is describe how plate motions have sculpted this landscape. And I'll invite you to look at the Red Sea and think about the same puzzling pieces that you saw when you were looking at the South Atlantic. And the Red Sea has a curious symmetrical character. The coastlines are fairly similar. And if you look at, you'll see a little ridge running down the middle of it. In fact, there's a rift valley down the central part of the Red Sea. And indeed, the margins of the Red Sea fit together. And as a student, a grad student with some of my colleagues who might be on the line, we used to actually cut out maps of the Red Sea and try to fit the coastlines together. And we used different kinds of maps. Some of them were geological, they had different projections. There was always some issues with it, but we were able to use that as an analog to show that it had rifted apart. And I think, Chun, let's just back out a second just to get this overview again, because I want to demonstrate a model that's a very sophisticated geological model here. And I'm going to, so get your view there of the Red Sea and the Gulf of Aden and the Arabian Peninsula. And then, Talia, I'm going to ask you to spotlight me a little bit. And I'm going to try and show you guys a model of this. And a little bit challenging to do, but you can see made out of paper here, the Mediterranean Ocean is over on which side? Right here. The Red Sea, the Arabian Peninsula. And what I'm going to do is if I can make this happen, I'm going to wiggle the system here, stand by for wiggle. And I want you to get a feeling that the Red Sea didn't used to be there. It was closed, sort of like that. And then it started to open in about 10 million years, 15 million years ago. And now it's open to about here. And it's continuing to open up about like that. So we're going to spend the evening or the next time talking about this phenomenon. So this is a model that I made just with paper. You can do the same thing at home. Any of you who are interested, pretty simple story. You just take a map and you can cut out the pieces and you'll make the story as we're describing it tonight. So as we look at the, let's come back to the scene. We'll come back to Chun's screen. And I want to emphasize that there's three different things going on here. As the plates are moving on the surface of the Earth, there's a region of extension where things are pulling apart. And that would be the Red Sea itself and the Gulf of Aden and down into the Afar Triangle, which you might take a quick peek at here in a minute. There's places where the plates are sliding past one another. They're literally sliding past one another. And that would be up in the Gulf of Aqaba and up at the Dead Sea. And then there's broad areas where the plates are smashing together, where there's compression or collision. And we're going to see that in the Zagros Mountains, and we'll look at it a little bit in the Oman area as well. So the three different styles, extension, strike slip, and compression, are going to be what we're going to be looking at in the course of the next few minutes. We'll start out with extension, and we can take a quick peek, Kachun, just at the Afar Triangle area, just to emphasize where the Earth is young, things are pulling apart. And as the Earth crust pulls apart, it's common to have volcanoes and eruptions of basalt magma, which is a dark colored magma. And here you're seeing, this is called the Afar Triangle. It's in Ethiopia and Eritrea. And the Gulf of Aden is on the right, the Red Sea is on the top. And this is called a triple junction. There's really three trends here because to the bottom of the screen is the main East African rift. The three zones come together in this one area, which we call the Afar Triangle. And it's called a triple junction because you get three different orientations of extension. But you can see the dark material here is volcanic rock. And the volcanic rock is basalt, and it's flowing from a series of volcanoes. The volcanoes are somewhat oval shaped, and the lava flows are the dark stains or the little trailing darknesses that come off. It's coming down into some sediment. There's a little bit of standing water. The floor of the Afar Depression is below sea level. Lots of salt deposits, and we call them evaporites in here. This is the Erta Ale volcano, and it's got a variety of craters that make it up, somewhat like some of the volcanoes on the Big Island of Hawaii, the long sort of rift zone kind of a setup. And Kachun is zooming in on the main crater, which is actually, it has a lava lake in the bottom of it. And we have seen some images over the years where you can see like hot lava in the bottom. These images, it looks like the surface of the lake is sort of cooled, so it's dark, but there's steam and sulfur, and you really feel like you're on the floor of the ocean here, looking at where the Earth is just forming. And it's literally the world is pulling apart here, and the lava is rising up along that zone of extension. As you pull the zone apart, you lower the pressure, and the magma is able to rise up from the upper mantle up through the crust. The crust is very thin here. And so here we're looking at the crater of Erta Ale. The place is very difficult to get to. I've never actually been here on the ground. It's a very inhospitable area, extremely difficult to get out into this country. But as we look around here, you'll see lots of examples of volcanoes, and you'll see also examples of faults where things are breaking. And we might look at a little bit to the southeast, and there's a series of very well-defined faults in this area. And you can see that the lava flows are literally being cracked by the forces of extension. So the takeaway message here is that we can go to places where the exposures are very good, and we can see the patterns and processes that in other places are obscured by sediment or obscured by overlying water. But there on the screen on the right-hand side, those linear features are cracks and faults where the Earth is literally spreading apart. And we've taken geodometers out here. Today we do it with GPS systems, and you can measure extension. In this area, the extension's on the order of millimeters per year, relatively slow. In other places, it's centimeters per year. These plates are moving at about the rate that your fingernails are growing or your hair is growing. So you might say, well, that's not very fast, but in these COVID times, I've had to have my wife cut my hair because it was growing so long that it was obscuring my vision. So these things do happen over the course of months. And of course, these plates have been moving for years, thousands of years, tens of thousands, in fact, millions of years. So the Red Sea, now we'll go up to the north end of the Red Sea. The Red Sea is about 15 to 20 million years old, and it's been pulling apart systematically. It's extending today. The Arabian Peninsula or the Arabian Plate is moving away from Africa. We're going up along the axis of the Red Sea. We're going to pause up in the Gulf of Aqaba. We've got Gulf of Suez straight ahead. Gulf of Aqaba is part of a strike-slip fault zone, and the Arabian Peninsula is sliding up. You might remember that little model I had. That's a zone of sliding. And literally, the Arabian Plate is moving to the north, and the Sinai Peninsula is staying put, relatively speaking. And we're going to zoom in. Let's go to that little there's a little fan delta there coming out into the Gulf of Aqaba. And I had a wonderful opportunity here with a geological study group from Denver a few years ago to visit this location. And fascinating geology, all kinds of evidence of extension, giant basalt dikes cutting the sandstones in the basement of the Sinai. And I went down onto the coast here. There's a combination of sand coming in and reef deposits, wonderful snorkeling and scuba diving here. And I was looking at this beach right there in the middle ground. And might be, Talia, you could bring me in again, because I've got a critter that I found on the beach, and I'm going to share him with you this evening. And he's just over my shoulder here.
We did actually get a question in the chat. Someone, Penelope, wondered, what is that snakeskin-like thing behind you? Well, Penelope, we're going to tell you.
So this is a mummified moray eel. And you can gaze into the maw of the mummified moray eel. And he's got a little beady eye. It's hard to see the little beady eye, but right about there is the little beady eye of this moray eel. And the teeth are all inclined backwards. Once you go into the mouth, you never come back out again. And pretty interesting. This is the Sinai is part of Egypt, and you're allowed to take one mummy back per trip. So I had this moray eel that I collected, and he's quite mummified. And I rolled him up a little bit and put him in my suitcase to bring him home. But then I had to resuscitate him once I got him home. And I had him in the bathtub resuscitating, and he wasn't resuscitating very well. So I borrowed some of Mary's, my wife's, special bath salts. And once I had the bath salts in there, the moray eel really puffed back out and came back almost to life. And I was able to stretch him back out, and he's done wonderfully well ever since. And my wife has always wondered what the ring around the bathtub was from that night. But she might be finding out tonight. I don't know if she's hearing the story, but.
I was going to say, Mary is watching tonight, Bob, so you be careful what you say. And I think I speak for us all when I say that your stories, whether it's, drinking margaritas on the rocks, like you said last time, or showing us your mummified eels, that's one of the best parts of these programs. So thanks for tuning in to Digital Earth, folks. You never quite know what you're going to get. Well, I'm going to switch back to Chun now. Is that where we'd like to go next?
Yeah, absolutely, yeah.
All right, thanks, Bob.
So the geology, of course, is wonderful here. We're looking at the edge of the Gulf of Aqaba, and some of you will remember that Aqaba is famous because Lawrence came in from the north side. We're about to go up. We're going to go up along the Gulf here. It has a strike slip fault on the bottom. The side on the right would be Saudi Arabia going up towards Jordan, and it's moving to the north relative to the left side, which here would be Egypt. And the strike slip fault comes out of the water near the town of Aqaba, which is where Lawrence came in from the north and surprised the people in Aqaba. If you haven't seen the movie Lawrence of Arabia, you have a wonderful treat. And that's Aqaba right there in the lower part of the screen. Now we're going to go up along the trace of the strike slip fault up towards the Dead Sea. And the geology here is a little bit subtle. You'll see some linear features associated with the strike slip faulting. Petra is just on the right-hand side for those of you who've been to Petra, but you'll see a little bit of elongated sort of north-south trending fracture zones and fault zones. And it's a fairly complicated area. There's a lot of different generations of faulting in here, but it is a big strike slip fault system. And up ahead is the Dead Sea coming into view. And at the south end of the Dead Sea, they're evaporating the salty water to make chemicals. They use the salt water, they evaporate it and they get potash salts and various different kinds of salts out of it. And it's a wonderful thing. And actually, just before we get to the Dead Sea, when I was here a few years ago, I was driving around this area and there's a giant pillar of salt on the south end of the Dead Sea. And that's Lot's wife. And some of you will remember, I think Lot's wife was leaving Sodom and she was admonished to never look back and never turn around. But she turned around and she looked back and she was turned into a pillar of salt. And when I was there, I was able to get actually a sample of her hair. So I've got again, might highlight me a little bit here, but this is a sample a lock of hair of Lot's wife. And she was some kind of a halite blonde, I guess. This is actually salt, and it's a piece of rock salt from Lot's wife, who's turned into a pillar of salt at the end of the Dead Sea. So if we now go back to the screen, we're going to see the Dead Sea. The Dead Sea is the lowest area on the surface of the Earth, and it's actually getting lower every year because the water is evaporating. And at one point, it was evaporating about 1 meter per year. So it was one of the things that was startling was that the lowest point on Earth was actually a changing number depending on what year you wanted to ask the question. They're actually contemplating putting in a canal from the Red Sea up to the Dead Sea to generate electricity and also to rehydrate the Dead Sea area. So it may be that in the near future, the water levels in the Dead Sea will come back up again. But right now they're low and falling. And you can see actually bathtub rings all around it. If you look closely at the edges of the Dead Sea, you'll see what look like bathtub rings because the water level has been falling consistently. We're going to keep on going north. We're going to follow up to the north end of the Dead Sea. For those of you who remember the Dead Sea Scrolls, we had a program there on the left-hand side. There's where the Dead Sea Scrolls were found. But we're going to find this river up ahead here. This is the sole inlet really into the Dead Sea, the significant inlet. There's a few small streams from Jordan. This is the Jordan River. And we're going to go up along the axis of the Jordan River, and we're going to see the Sea of Galilee coming up, which is sort of a lake. It's Lake Galilee. But water is a huge problem in this area, and the water levels are falling in the Dead Sea because the water that used to feed it from the Jordan River is largely being used for irrigation. So there's a lot of irrigation along the margins of the Jordan River, with the net result that very little water gets into the Dead Sea, and consequently the water levels there are falling. Again, strike slip fault, the area on the right is moving to the north relative to the area on the left. And you can see this long linear feature right here as we go up towards the Sea of Galilee. So a very active area. These faults are moving today. There's frequent earthquakes in this area, very dynamic. The Sea of Galilee coming up here, shallow lake really, source of water for the surrounding territory. And there's been a lot of concern the Lake Galilee has fallen also in elevation over the years. And it depends a little bit on the snowfall and the rain in the Hebron Mountains up to the north. But this lake is a very important source of water for the region. And it's a very threatened area. The lake is relatively shallow, and there's a lot of concern about its water level. But we're going to keep on, we're going to follow our thread of tectonics here. And I want to scoot up along the north end. We're going to leave the area of Israel and the West Bank. We're coming into Syria. We'll have Lebanon up to the upper left. And we've got a series of folds, rumpled ground. You see them up ahead. This is called the Palmyran Fold Belt. We're not too far from Damascus right here. And these folds are partly reflecting the fact that the trends are turning as we go north, arcing towards the east. And we're going to be heading up towards, through Syria over towards Iraq and towards the Zagros Mountains, which is going to be the focus of our next few minutes of discussion. So we're going to see up ahead coming in the Euphrates River. We'll see the Tigris River in a few minutes, and we're going to arc around over the top of Baghdad and head over towards the Zagros Mountains. Again, remembering on our diagram, this would be the right-hand side. And so we could even scooch out a little bit, Kachun, just to give everybody a reminder of where we are in terms of the overall geometry. This is an area we're not all that familiar with. And you'll see the Tigris River on the bottom, the Euphrates River on the bottom, the Tigris River on the top. They come together near the town of Baghdad, and they collectively feed the north end of the Persian Gulf. So we've got the geometry now. You've got the Mediterranean on the upper left, the Caspian on the top, the Black Sea on the upper left, the Caspian on the top, Mediterranean on the lower left with Cyprus in it. And then you've got the Persian Gulf on the right. And we're going to now zoom back in. And I want you to look at the compressional areas now. Remember, the Arabian plate is moving to the northeast, and it's causing compression or folding. And a lot of these hills in this area. It's called the Zagros Mountains. A lot of these mountain ranges are very elongated, meaning they're long, and they look like the folds of a carpet, or if you took a wet paper towel and pushed it, you'd create some of the same kinds of geometries that we see in this area. And we're going to look at a couple of really good examples that Chun and I have prospected for, but there's lots to choose from in here. You can't go wrong. If you scooch into this area on Google Earth, for example, you'll be able to see a lot of these features yourself, and you can do this yourself at home. We're going to pick a couple of highlights and just to illustrate what these fold patterns look like. And again, the resistant rocks in this area actually are mostly limestones, and the limestones form big flat irons. You'll see some patterns that will remind you of the flat irons. Those of you from the Colorado area, they'll remind you of the flat irons behind Boulder. And these are very young anticlines. They're still folding today. So we call them anticlines. That's the name for a positive fold. And they're deforming even today. There'll be earthquakes out here. It's tectonically active. There's both faults and folds. And the ground is very rugged. It's pretty arid. We're in a pretty arid ground. We're not too far from Persepolis. The ground where Darius and Alexander fought is just near here. The town of Shiraz is up in this country. So they grow wonderful grapes, historically wonderful grapes. We had a digital Earth on the history of grapes at one point, or the history of Shiraz wine, and we featured this area at one point. One of the things that's interesting about the geology is that the resistant beds are the limestones. The less resistant ones tend to be mudstones or sandstones. And then there's a very curious additional material here, which we're coming up on in a moment. And I'm going to remind you of Lot's wife. And you'll remember Lot's wife was made out of salt. And in fact, in this area, long, long time ago, 500 million years ago, when an ocean was just forming here, there was a series of salt deposits laid down called the Hormuz Salt. And the Hormuz salt's at the bottom of this whole system. And as it gets squished and squunched, the salt is being pushed out through some, we call them diapirs, but there are areas where the salt is rising to the surface. And the dark colored material that you're seeing here in the foreground is, looks like lava. You might remember that from the Afar Depression, but this isn't lava. This is actually salt. And the salt is white on the inside, but it gets a very dark crust on it. So it looks very black. You'll see some of the drainages are quite pale because they've got salt incrustations, but this is actually a salt dome coming up, and it's flowing off to the sides. You literally have salt glaciers in this area. Glaciers made out of salt, a curious idea. See how it's flowing down the sides of the mountain there? And we've got a couple other examples we've picked out to show you. This is just one of probably 20 or 30 of these features that are well exposed, and you'll see them if you poke around on Google Earth. They're quite visible as dark features. We'll look at a couple others.
One quick question, Bob. What were those mountains called? I do see one question.
Okay. Yeah, the mountains are called, yeah, absolutely. The mountains are called the Zagros Mountains, which begins with a Z, so Z-A-G-R-O-S. And you'll see some wonderful things. There's a lot of organic material in these sedimentary rocks that have been deeply buried and squished. And of course, you'll all be familiar with the fact that there's a lot of oil in this area. There's oil not only in some of these hills in front of us, but a lot of the oil is migrated up onto the Arabian Shield. And some of the largest oil fields in the world, in fact, the largest oil fields in the world, are up on the Arabian Peninsula. And the oil is derived from a variety of organic rich rocks that are being compressed and heated in the Zagros area, in the bottom of the basin here. It's called the Persian Gulf Basin. But let's take a quick look at these other, couple of these other salt features here. And you'll appreciate the beautiful folded nature of the rocks. And this would be a wonderful place to be a geologist, but there's so many mountains, it'd be a challenge to figure out how you map them all. And space imagery is actually the answer. The answer to get a good map in this area, you look at satellite images, and you'd be able to make yourself a map. Here again, this feature, I think you'll all appreciate as it gets into focus. It's coming from the top of the screen and flowing towards the bottom. And it's literally a mass of salt that is extruding onto the Earth's surface and flowing downhill. And it'd be awkward to be a little villager down there trying to organize your crops, and you've got this salt glacier that keeps flowing down the mountain towards you. But that's the part of the challenges of the people who are living in this region. And again, well, there's maybe another little beautiful one off to the right we'll take a quick look at. But you can pick these, you'll start to see the dark color, almost a purplish color. You'll start to appreciate it. And you'll come in here and you'll see there's another feature up ahead. It's just a little bit to the right, I think. Yeah. And there you're seeing, again, a central source. And there's a question about how does salt flow? And salt is we think of it as a rock, we think of it as a solid, but it's relatively plastic. And in fact, in many of the salt mines around the world, you'll actually see the deformation in the walls of the salt mine. And there are cases where the salt buckles and folds. And so it moves slowly. And again, at any instant in time, you don't see very much, but it is actually a plastic type material. And just like ice, you might think of a piece of ice as being relatively solid, but ice also flows, as you know, in glaciers. Now we're going to take one more look here at the effect of compression, and we're going to drop down into the area of Oman and the United Arab Emirates. And I think, again, this is a different situation, but it's a place, again, where compression has modified the face of the Earth. And you'll see down here a very dark colored material. This is we just crossed the Straits of Hormuz. This is the Indian Ocean on the right, and the Persian Gulf is up on the left. And the dark material in here is basaltic material. It's got a fancy name. We call it ophiolite, which means snake-like texture. And a lot of these basalts have a very gnarly kind of surface to them. And they thought it looked like snake, so it's called ophiolite. And it's a dark material. We've studied it a lot, and there's some very interesting features in it. It has pillows, which are basalt. It's a shape of basalt that flows into water. So we've observed this in many views in Hawaii and underwater photography. As the basalt flows out of a volcano into the ocean, into water, it'll often make pillow-shaped things. They're actually made of lots of elongated trunk-like things that when seen in cross-section, they look like pillows. We call it pillow basalt. And this ground is full of pillow basalt, definitely was deposited on the floor of the ocean. And because of the forces of compression, it has been lifted up and put onto the continental crust. So the process is called abduction. There's a fancy word for it, which is as opposed to subduction, where something goes down. Abduction is where something comes up and over. And this is oceanic crust that has come up and over and onto the land. And my son and I were out here wandering around at one point. We were actually he was looking at water and water resources associated with date farming in the United Arab Emirates, in Ras Al Khaimah in particular. And we spent a night out on this ophiolite here, and we're able to use the pillows as pillows. So the pillow basalt served as pillows for our heads as we were in this country. And one of the things, it's of course a very beautiful, rugged land, very dry, very arid. Water is a precious, precious commodity out here. And it's a land that's been changing dramatically. People have gone from being growers of dates and herders of animals. Now they're living in cities, gleaming cities like Dubai, some of you might have been to. And the same is true in Sharjah and Ras Al Khaimah, the Emirates. It's a very modern part of the world. And the old traditions are slowly falling away. Things like growing date palms, which require a lot of work and a lot of water. It's a dying art. And then as we zoom in here, we'll see some of the rugged ground in Ras Al Khaimah. And these are uplifted mountains associated with compression, collision. And this Ras Al Khaimah actually has a source of gravel and building stone, and the other emirates have lots of oil and gas, and Ras Al Khaimah has lots of building stone, and there's big quarries up in this country where they mine the rock, making cement and making building stone. And I drove up this switchback road here at one point, and I got up to the very top of the switchback road and was looking up at the very top. You'll see it coming into the view, looking at the magnificent scenery of these giant uplifted mountains. And to my astonishment, I was approached by a goat. And I've got 3 goats here in Longmont, so I'm partial to goats. They're my friends. So I sort of said hi to the goat, and I asked the goat what the goat was up to, and the goat says, "Well, I'm here reporting for duty. What am I supposed to do?" And I said to the goat, I says, "Well, I don't know. I'm a tourist. I'm just here to admire the scenery. I don't know what you're supposed to do." But there's the goat. You can see that nice goat with the nice floppy ears. And he came right up to me. You see my feet in the foreground of the image there, and the goat came right up. And I realized that the goat was unemployed. And I said, "Oh my gosh, you must be one of these abandoned goats." And the people who used to herd goats have all gone to live in cities. They're driving fancy cars. They're living in air-conditioned houses. And the goats have been left wandering the hills, sort of wondering what they're supposed to do. So I offered solace to the goat, but I had no employment for him. So the goat and I had a little bit of a conversation, and then we went our separate ways. So we'll back out here. There you can see where we are. And we'll back up, and we're going to go over to the east, and we're going to carry a toolkit with us now, understanding plate movements and plate interactions. So I'm thinking about the forces of collision. I'm thinking about the forces of strike-slip motion or sliding motion. You'll see this whole ground is compressed. We might stop at that beautiful place where there's some folds. Kuchin, I don't know if you can see that. It's sort of on the central part of the screen there. There's a lot of deformation in here, a lot of folding. Almost wherever you land, you'll see deformation and folding. But we're coming across Afghanistan, and we're up against the edge of coming into Pakistan, and you'll see a north-south feature here. And again, we might back out a teensy bit to Kachin just so that we can keep our bearings. And it's a great big fault, and you'll now all start to feel the same patterns. We've talked about this before, long, elongated, straight fault, and we've got Pakistan and India on the right and Afghanistan on the left, and right in the middle is a big north-south line, and that north-south line represents what we call it a strike-slip fault. It's actually the Chaman fault, and the area on the right is moving to the north. The area on the left is moving relatively to the south, and the whole business is moving because the Indian plate, which is to the right, is crashing up into the Himalaya mountains in the north, and that's the plate boundary. There's also a boundary, you can see sort of an east-west feature in the middle of the screen, and that's called the Herat fault. It's also a strike-slip fault, and the middle triangular zone is actually being squeezed out to the left. So as the Indian plate is moving up from the right to the north, it's smashing into Eurasia, and Afghanistan is actually trying to get out of the way. We call it an escape block. So the Chaman fault is the one on the right, the Herat fault is the one that's going east-west along the middle part of the screen, and the bulk of Afghanistan is being squeezed out to the lower left. And that's actively happening today. This is active tectonics happening today. And there's earthquakes in this area all the time. We're going to move to the right, to the east. We're going to cross the plate boundary into Pakistan. We're seeing the Himalaya Mountains. We're just going to take a quick look at this basin right here coming in on the upper right. It's the Kashmir Basin. And we're just going to admire one of the great, beautiful places in the world. And it's, again, a result of compression. The system is squashing. You can see the folds on the lower left. The whole business is pushing to the upper right. And the Kashmir Basin, we call it a piggyback basin. It's riding on top of the series of faults and folds. And it's got internal drainage, which pops out to the north, forming the Jhelum River. But it's a very young basin. It's only about 4 million years old. And it's because of the compression of the Himalayan foothills that this basin has been preserved here. And of course, it's relatively high elevation. It's beautifully cool, wonderfully green. And of course, if you live down in India and northern Pakistan, the idea of coming to the beautiful green valley is a wonderful thing. And many, many people have gone on vacation to go up into the Kashmir Valley. Of course, it's a very coveted place, and one where there's a lot of conflict between India and Pakistan, trying to figure out who has the rights and authority in this area. It's somewhat disputed ground, but it nominally is controlled by India. And if you travel here, you can go to Wular Lake, which is coming up on the distance, and people live in houseboats. There's a series of hotels that are actually houseboats, so you can stay in a houseboat in Kashmir. It's a wonderful thing. So we'll take a look at Wular Lake just up ahead, and then we're gonna back out, and I'm just gonna prepare you for the next spot, which is sort of the final part from my presentation. We're gonna, as we leave Asia, we're gonna go back to North America. There's Wular Lake and houseboats, the Valley of Kashmir. And we're going to take an overview look at the North American region. And I want you to use the tools that we've talked about in terms of understanding the plate configuration for the United States and for North America. And of course, I'm speaking to you from Colorado, so we're in the middle of the continent, if it were. But as we get the overview of North America here, I'm going to be asking about the plate boundaries. So remember, we're talking about these semi-rigid plates that are drifting around on the surface of the planet. And the first question I'm going to ask is, where is the eastern plate margin of the United States or the North American plate? So where is the eastern plate margin? And I'm going to pause a little bit as you noodle on that, and I'm going to hopefully see some answers in the chat box. But so the area on the eastern seaboard, you'll see the coastline, then you'll see the continental shelf, and then you'll see the continental slope. And the question about why the ocean changes color, which I'm seeing in the chat group, it's really a function of the depth of the water. So the way this has been set up, the shallowest water shows up in the lighter colors, the pale blues, and then the deeper water is showing up as the darker blues, almost purple colors. And the question about where is the plate margin, I'm seeing the right answer coming from Rick O. He's got the right answer. Other people maybe coming up with the right answer. I see a few more people answering. I see a few guesses coming in. People are making what we call WAG, wild ink guesses. Well, so the plate margin, you got to think about where active tectonics is happening. Active tectonics, in other words, where the Earth is moving or breaking. And on the eastern side of the U.S., if you think about the cities of the coastline, Washington, D.C., Newport, Charlottesville, going down to Florida, they're very, there's no earthquakes. I mean, there are very few earthquakes. And this is quite peaceful in this area on the east side of the United States. The activity is actually happening way out on the right-hand side of your screen. Well, Eric got the right answer. There you go. It's the Mid-Atlantic Ridge. So the eastern side of the plate that we live on in the United States and North America is all the way out on the Mid-Atlantic Ridge. And if you want to see what it looks like in detail, you actually have to go to Iceland, which we've talked about in some other digital Earth programs. And in Iceland, you can actually see what the Mid-Atlantic Ridge looks like. The Mid-Atlantic Ridge would be the eastern plate margin. So now if we go back to the entire North American plate, and again, I want to get the feeling for the whole business. So many of us are living in the Rocky Mountains in Colorado, sort of in the middle of that scene. And the plate margin on the east is a long way out there in the mid-ocean, mid-Atlantic Ocean. The plate margin on the west, however, is not that far away from us. And if we go down to the Gulf of California, Kachun, let's just take a little look down there. And I'm going to ask you to remember what we talked about in the Red Sea. And if you look at the Gulf of California, I hope you'll see some similarities to the Red Sea. It's got very discrete margins, and I'm looking at the Sea of Cortez, or the Gulf of California now, and it's got a rift valley in the bottom of it, which is somewhat oblique. The system's pulling apart obliquely, but there's a rift valley in the floor of the Gulf of California, and people have dived down there. There's hot springs. There's all kinds of activity associated with volcanoes, little volcanoes, and it's actually pulling apart, much like the Red Sea is. And the Baja California Peninsula has been broken away from what's here Mexico, and it's being pulled up towards the upper left, away from Mexico. And as we come up here to the mouth of the Colorado River, up at the north end of the Gulf of California, or the Sea of Cortez, as it's called, we'll come into view. We'll have the Salton Sea coming up ahead, and that's the boundary between Mexico and the United States. And this area has a long series of faults along it, and these faults are elongated, linear. They were mapped as individual strands back in the 1940s and 50s, and in the 1960s, geologists were working out here starting to suspect that there was a long linear fault that ran up along the entire coast of California, and it really was in the tail end of the 1960s that this fault was recognized for what it is. And of course, this fault, many of you guessed it, is the fault that's behind Talia on her screen. This is the San Andreas Fault. And it is a plate margin. The area to the left or to the west would be part of the Pacific Plate. The area to the right would be the North American Plate. And the boundary, which is the linear feature right in the central part of the screen here, is the San Andreas Fault. And we're going to trace it right up along the length here. We've got to scooch a little bit to the left, and it's going to come up through the town of Hollister, which is right in the foreground, the Monterey Bay to the left, the San Francisco Bay coming up into view, and the currently active strand of the San Andreas Fault is just on the west-hand side of the San Francisco Bay. Here it is right in the foreground. And there's a series of strands. So there's the active fault is the San Andreas, but there's several others that are, in some cases, still a little bit active. And this fault system is moving at centimeters per year. In the San Francisco area, the fault is locked. It's not moving at all. It's building up stress right now. And of course, every 100 years or so, it moves. And part of our life on the planet is the fact that we live on a moving planet. And there will be another fault break here on the San Andreas at some point in the future. And many seismologists, of course, are trying to study when that will be. It's one of the great quests to try to predict faults and fault motion. We can understand their distribution pretty well, but when they're going to break remains a great challenge to Earth scientists, one of the great challenges that we face. As we move up along the length of the fault, we've left the San Francisco area. We're going up into Northern California, heading up towards Cape Mendocino. And up at Cape Mendocino, which is coming up in the near foreground, the San Andreas Fault goes out to sea, and there's something called there's a Mendocino fracture zone. And this is an area where there's a transition in the tectonic style. It's right up there in the top of the screen there, actually. And it's another place where it's effectively a triple junction. The Pacific Plate is moving up towards the north, and we cross a big transfer fault or transform fault here. And above it to the north is a small plate that is actually subducting or going down under Western North America. So we're going to change the style as we move up past this Cape Mendocino. We go into an area where it's called the Juan de Fuca Plate. There's mid-ocean ridge spreading on the left. The plate is moving to the right, and it's going down underneath the Cascades. There's some folds right in the central part of your screen. You can see the effects of compression. Remember, we talked about compression both in the Zagros and in the Kashmir area. And this is a place of compression. And then the ocean plate is going down underneath the continental plate here, and it melts, and the white spots are the Cascade volcanoes. So as the material goes down under a process called subduction, the material gets hotter and hotter, and it's got some water with it. It's carrying water and hydrated minerals, and they go down there, they get to a certain depth, and they melt, and the melt rises. And similar to the salt that was rising over in the Zagros, but here the magma is rising from greater depth, and it forms, of course, the bowels of these volcanoes, which you can see so nicely as a little string of white pearls running up along the Cascades. And many of you have seen those volcanoes. We talked about Mount St. Helens in one of our earlier presentations. So let's back out and we'll see all of North America, and I'll summarize it, and then I'll turn the microphone over to Chun. But just as we leave North America, I want you to, again, appreciate that we live on a moving plate. The plate margins are the Mid-Atlantic Ridge on the east, the San Andreas Fault and the Cascades Subduction Zone on the west, and that we ride, all of us, as passengers on the plate. In fact, all of us on Earth, 7.5 billion of us, are riding as passengers on the plates. And the plates are moving, and we will feel their motions from time to time. So I'll turn the microphone over to Chun, and we'll admire the pale blue dot, the only dot we've got.
Thank you very much, Bob. So we mentioned earlier that we weren't going to just stick with planet Earth, that we were going to go off planet and go elsewhere in the solar system. And I guess we only have a few seconds to do a quick poll, but if you have a guess as to where we might be headed next, that is tectonically active and where we can talk about some of the same types of phenomena that Bob talked about on the Earth, please mention them on the chat.
I see. I don't
yeah,
interrupt.
definitely got it. We have one person who's got it.
Chun, you can see the dust coming off of Africa. I just want to shout at the dust.
Yeah, you can see the dust plume. This was taken last week, so you can see the dust plume crossing the Atlantic. All right, so it looks like we have a lot of guesses from Mars, a couple for Venus, as well as the moon, and I even see Io, which is a moon of Jupiter. But the correct answer is actually the moon of Jupiter, Europa, and there were a handful of people who got that correct, so congratulations. And we were flying, just covered about 5 astronomical units in a few seconds, so going much faster than the speed of light to get to the moon of Europa. Europa is one of the 4 large Galilean moons of Jupiter. These are icy moons for the most part. Europa is slightly smaller than our moon. And when our first high resolution spacecraft encounters of Europa passed by, we discovered that Europa was very bright, very white colored. So that hints at the surface that's covered in ice. But what was really remarkable is that Europa doesn't really have any craters. You see a large crater with some rays, light-colored rays radiating outwards, but there are very few craters on Europa compared to the other Galilean moons, or to the other moons of Jupiter, and especially our moon. And so that suggests that something is erasing the craters over time. And we think that Europa's surface is probably no more than about 60 million years old, because there's something actively erasing, covering over the craters. And the other remarkable thing about Europa is that there are these long ridges or lines that cover the surface. And these are really remarkable. And what we realize is going on with Europa is that Europa doesn't have a completely circular orbit, it has an elliptical orbit around Jupiter. So sometimes it's slightly closer to Jupiter than at other times. And as a result, the amount of gravity that Europa feels from Jupiter changes. And this changing gravity manages to stretch or distort the moon. And it's what we call a tidal force. And as a result, what happens is Europa gets stretched. And if you imagine playing with silly putty, and you start stretching it, you actually feel the silly putty heat up. And so we think what has happened is that as a result of these tidal forces from Jupiter, not only from the pull of Jupiter, but also from some of the other large moons that are orbiting Jupiter. Europa is heated up on the inside so that the outer crust is made up of a crust of water ice, but we probably think that there is an interior subsurface ocean of water underneath that surface ice. And so all these cracks that you're seeing is the result of the fact that Europa is being tugged on by Jupiter, and the surface has broken up, and over the course of the orbit, the surface gets pulled in different directions. And so a lot of the same phenomena that Bob has talked about, the idea of extension, the idea of faults on the surface of the Earth, we see very similar types of features on Europa, but they are also very unique because we're seeing them on a surface made up of ice with an ocean of water underneath, as opposed to a surface made up of rock. And so here we have a break spreading event where you see there's a dark diagonal band of faults that is running diagonally from the upper left to the lower right. And then you also see these very thin whitish streaks that are running kind of horizontally perpendicular to that broad dark diagonal. And so what we're seeing is the beginning of a pair of faults that are opening up. And just like we can see on the Earth, where in places where the Earth is extending or spreading apart, here we have faults that are spreading apart, and you can see that they're breaking through that dark band of other material. And then if we zoom out, I'm going to see if I can find this other region. Here we go. And so this particular part isn't quite as high resolution, but you can see, I'm going to zoom in to another dark band that's running kind of horizontally across the screen, and it kind of curves. And what I'm going to do is show you a much higher resolution image. And so the image, you can see that this band on the north and the south sides is equivalent to Africa and South America spreading apart, because you can make out that the borders of those bands, like the continents or like at the Red Sea, they sort of mimic each other, they mirror each other. And so what we think is happening is that that dark band is causing the crust to spread apart. And you can even see that there are horizontal faults that run vertically, and you can trace them between the top and bottom halves in that picture on the left. And on the picture on the right, planetary geologists have basically cut along that dark band, and they've glued the picture back together, showing how the two really fit together really well. And so this is evidence that Europa is pulling itself apart, that there are lots of extensional features on its surface, just like we see on the Earth. And what's really curious is that unlike the Earth, where parts of the Earth are subducting, meaning they're pushing back underneath themselves, one plate underneath another, there's really no evidence of subduction on Europa. And we only see evidence of stuff pulling or extending apart. And so that could be evidence that as the water ocean underneath Europa slowly freezes, of course, ice expands as it freezes. And so Europa is slowly expanding and increasing in size over time. And the evidence of that are all of these extensional features. All right, so with that, that's our little off-Earth segue. And I think that is the end of the main part of our Digital Earth program. And Bob and I are happy to answer questions from everyone out there. So thanks a lot.
Indeed. Thank you both for that incredible presentation. I am going to stop the spotlight on Chun and put us in gallery view so that we can get a view of all of us. It looks like Lorianne says, thank you for the bonus space treat. Yes, Lorianne, we love any opportunity to take you off planet. As I mentioned at the beginning, traveling isn't really a responsible thing for us to be doing at the moment. So we're really excited that not only can we show you places on Earth and even close to our own communities that we can't physically get to right now, but we can also take you to more exotic places. So we're really happy that several of you have decided to stick with us. We know we're past our 8 o'clock end time. Typically, we usually end these programs at about 8, but we had so much cool stuff that we wanted to show you tonight that we are running long. So thank you for sticking with us. I did see some questions that I would like to pull to ask our experts now. Let me see. We have lots of them coming in. Thanks for hanging with me while I find some questions. I did see a question wondering about how plate tectonics got started. Is this something that's always been active on our planet? Maybe what caused it to get started as our Earth formed? Can you talk a little bit about the origins of plate tectonics, Bob?
Well, that's a good question, and one that, of course, a lot of geologists have been asking for years. Once they figured out the continental drift paradigm, or the plate tectonics paradigm, it allowed us to organize our thinking about the geology of oil and gas and ore deposits and other earth materials. So the question about, well, how old are the plates? How many plates are there is a deeply concerning question. We can definitely see it going back over 1 billion years, meaning 1,000 million years. And as we go back that far back in time, the geology is obscured by the actual forces of plate tectonics, which are continually moving the pieces around and recycling and grinding them. So if we look at the old part of the Canadian Shield, parts of Western Australia, parts of Southern Africa, we see these cratonic nuclei, we call them, and they're in excess of 1 billion years old. So we're quite sure that plate tectonics has been going on in some fashion for over 1 billion years. Before that, the Earth's history is a little bit mysterious. There's different people that would extrapolate back. If we go back far enough in time, of course, the Earth's surface was thought to be largely molten. So as the Earth cooled, the idea was that the crust was comprised of more rigid material. And then as the upper part of the mantle was losing temperature, there was convection that would have been active. And it's those convective forces that are moving the plates, and it's quite likely that they go back well more than 1 billion years.
Very good. Bob, just a note for you, you are getting a little bit quiet. You might want to make sure that the microphone on your headphones is close to your mouth.
It fell.
A quick note from your good old host here.
I need to have my prehensile ear so that it holds.
That would be a good idea. Question from Debbie, and I never realized that I wanted to know this until she asked it. If water and sea levels are changing all over the world, where is zero altitude located? I know we made several references to things like altitude and the Dead Sea being really low in altitude. How do we decide where zero is? That's a great question.
Yeah, so we refer to that as the geoid, and it is a super interesting question. And I used to think that sea level was a universal thing at zero. I thought that it was always that. And then at one point, not that long ago, I saw a topographic map of the ocean surfaces derived from satellite measurements. And there's an astonishing variety of topography on the ocean, believe it or not. And it's because the wind is pushing the water, tides, of course, are moving the water, and so you get a considerable amount of topography. If there were to be no forces acting on the ocean, if the Earth were not spinning, and if the wind were not blowing, presumably the ocean would settle down to a uniform elevation that we might call sea level. But if you go to a lake or something like the Dead Sea, of course, that's not connected to the ocean. So the Dead Sea, the level is falling because the water is evaporating faster than it's coming in. Sea level around the world is rising at about 3 millimeters per year because of the melting of ice that's on land and the thermal expansion of the water. So sea level is actually rising because of climate change, and 3 millimeters a year doesn't seem like very much to me as a person, but as a geologist, 3 millimeters a year is huge. So sea level is a very dynamic concept. Thank you for the question.
Yeah, good question. Sounds like it's not an easy one to answer. A question from Josh, and I remember this one came in while we were talking about the San Andreas Fault specifically, talking about the movement of faults and plates against one another, above each other, under each other. You mentioned centimeters per year, you know, the number of centimeters per year that things might move. Is that an average? And do these plates only move during things like earthquakes or other similar events, or do they move constantly?
Yeah, so super good question, and one that we fussed about it a lot. And it's been my great joy to live in a time where questions like that get answered by data. So we have a wonderful array of GPS sites set up around the world, and of course in Western North America, a tremendous number of them. And we can actually map the way things are moving today. In the past, we sort of speculated and people made averages based on the age of a volcano or something. There were some average numbers. But today, we can actually measure it. And it's complicated. I mean, if you go to California, for example, and look at the deformation along the San Andreas Fault, the fact that there are multiple strands is an issue. Some of the strand meaning that some of the portions of the fault are very well mapped, others are not so well mapped, and there are centimeters of displacement between North America and the Pacific Plate, but where those centimeters of displacement are actually taking place varies a little bit depending on where you are and which fault is active. And in some places, the faults are moving all the time. The little town of Hollister, south of San Jose, it's moving all the time. You can go to that town and you'll see the sidewalks broken. You'll see cracks extending across people's driveways. The fault is moving all the time. If you go north to San Francisco, I mentioned it quickly, but the fault is stuck. It's holding there. The last time it moved was about 1906. And we think that it moves about every 100 years. So it has pent up meters of offset. And when the fault next moves in the San Francisco area, in the Bay Area, it's likely to have meters of offset, 3 feet, 6 feet of offset, which is going to be a tremendously big earthquake. So a lot of us who talk about the plate tectonic patterns of the world recognize that there are these dangerous areas. And frankly, the Bay Area is a dangerous area. We know that there will be earthquakes. We know there can be very big earthquakes. It's not the only place. There are other places around the world that have the same kind of challenge, but it's a very interesting area. And of course, the bottom line is here's where science can help people, and it has. I mean, there's been a huge amount of effort put into the construction of the infrastructure in the Bay Area to prepare for shaking. So those of you from California will be familiar with the preparations that have been taking place over the years to make our infrastructure as resilient as possible in the face of earthquakes.
Maybe this is a topic for a future program, but that's just making me think about how many events like this might have gone into the breaking up of Pangea. That's inspiring many questions. So maybe that'll be a presentation for a future date. I think we have time for one more question, and then we can read out our haikus. And this one I'm actually going to give to Kachun. Kachun, we do have a question from Glenn and Jane wondering if we were on the surface of Europa, would we hear the ice pulling apart like glaciers calving? Now I want to know the answer to that question.
Well, the immediate answer is that you wouldn't be hearing anything at all because there's not much of an atmosphere on Europa. So you won't have any sound traveling without air to carry the sound waves. And I don't, I'm not a planetary geologist, so I'm guessing that the processes that are occurring might be too slow to create noticeable sounds. What is really interesting is that Europa takes about 85 hours to orbit Jupiter, and there's actually quite a lot of evidence that some of these faults can actually occur on cycles that occur every orbit. So basically every 85 hours, so less than 4 days. And so the ice is, the faults are active even today. And whether, if you went to Europa and put a stethoscope up to a block of ice, whether you would hear it moving as Jupiter's tides are causing those faults to move, that's an open question for the planetary geologists.
Sounds like we might need someone to go answer that one someday. Bob?
Yeah, I'm going to just jump in a second, guys. I know there's a question in the chat group, and it was about sea level changing through time. And we have to appreciate that as the continents have been shifting around, there are times when there's many different continents broken apart. Then there's times when they're assembled, for example, in Pangaea, when they were all assembled together. And that has an effect on sea level overall. And then there was a question about how do we reference the elevation of mountains? And I tell this a little bit as a joke, but bear with me. In Colorado, we're very proud of our 14,000 foot peaks, of which we've got 53 or 52 or whatever that number is. And some of those 14,000 foot peaks, many of you will know this from having climbed up on them, they're only 14,001 foot high. And there's 14,002 and 14,006 and things like that. And as sea level is rising, that's the basis from which we measure elevation. So in principle, we're at risk of losing some of our 14ers. And the students from the School of Mines have gotten onto this, and they're very alert and worried about it. And they've been carrying rocks up to the tops of these mountains to try to make sure that they stay up above 14,000 foot. So that's just a little bit of a tongue-in-cheek comment.
A little bit of a tradition. All right, that is all the time we have for questions. We're sorry if we didn't get to all of them. We did have a lot of them, and we had a lot to show you tonight, but I do want to end our evening with 2 haikus. We got 2 this time. Well, we got 1 at the very beginning, but we have since gotten 2 more. And the haiku writers are growing in number. We didn't get one from Judy tonight, but we did get one from Marissa, who is 10 years old. Marissa's haiku is, "Grumble, says the earth. Suddenly, a crack is here. Creak, groan, says the earth." Way to go, Marissa. We love that you were inspired. And then one from, I think, Dave saying, "Sure, Io is cool. It even has volcanoes, but it has no plates." All right, that is all the time that we have tonight, folks. Thank you so much for tuning in for another edition of Digital Earth. Again, this was a topic that we selected from your ideas. A few weeks ago, we sent out a little poll saying, what would you like us to talk about in the future? So if you have any further ideas, you're welcome to send them along to the museum. Send them to us on Facebook, tweet us on Twitter. If you're members, you can email membership, or you can even email them to me, virtual@dmns.org. We would love to hear your ideas. You never know, you might see your ideas in a future session, but we are looking forward to keeping these going, even though our museum's doors are open now. So you can get your tickets to come pay us a visit in person. Who knows, you might even see one of the 3 of us. DMNS.org is how you can reserve your tickets to come on in. Otherwise, we'll keep seeing you on Wednesdays. So we're so excited and grateful that you've decided to tune in. Again, my name is Talia. Your experts this evening were Dr. Bob Raynolds and Dr. Chun Yu. We are so grateful that we had you all, and we'll see you next time. Bye, everybody.
Good night, everyone.
Good night. Goodbye.